Hello everybody, hope you're doing well. This is paper 2 from November 2023 and this is time zone 1. Now let's have a look at it and see what we can do. Question 2 is 15 marks. Let's see what we can do. Ansel is designing a racing track for a local bicycle club. The following diagram shows an incomplete portion of the track. Ansel wants to design the track such that the inner edge is a smooth curve from point A to point B, and the other edge is a smooth curve from point C to point D. So smooth kind of curve from point C to D and from A to B. So it wants to complete this bicycle track. The distance between point A and point B is 90 meters. To create a smooth curve, Ansel first walks to point M. So here he is, he's walking to point M. Write down the length of BM. So BM is going to be, use a different color, BM is going to be this distance right here. And so if 90 is the total, halfway through is just 45 meters. Okay. Alright, and likely we're going to need to make use of that. Ansel then walks 32 meters in a direction that is perpendicular to AB to get from point M to point E. Point E is the center of a circle whose arc will form the smooth curve between A and B on the track as shown in the following diagram, and it's down here. Okay, so let's mark that up actually. We found that the distance from B to M was 45, and we were told that he walks a perpendicular distance of 32 meters. So perpendicular will just be a right angle. Right? Alright, so we know this is a right angle, it's perpendicular, and he's walking 32 meters. Okay, now we want to find the length of BE right here, so the line segment BE. Let's go ahead and work that out. Since we have a right angle triangle here, we should be able to use the Pythagorean theorem. And let's call it x for now. Let's call it actually, don't want to over-determine or over-define our variables. But let's just call it x. I think that should be fine. So what do we know? Our Pythagorean theorem, I'm going to throw around the variables a little. Our Pythagorean theorem is a squared plus b squared equals c squared. And this actually is not given in the formula booklet, but if we have some right angle triangle, and this is A and this is B, this is our longest side. So what we're saying is the square of the two shorter sides, if we sum them or add them together, it'll equal the square of the longer side. And our hypotenuse is always the longest side. So let's go ahead and work that out to find the length of BE. So we have 45 squared plus 32 squared, and that should equal to, in this case we called it x, so let's write it as our unknown, our x squared. Okay, we can end solve this, or we can just essentially take the square root of all of this, and then that will be equal to x. So both will give us the same answer. Let's go ahead, so it's a little unclear, let's go ahead and put this into the calculator. Alright, so we have 45 squared plus 32 squared, and then we want to take the square root of the answer, or all of that, this 3049. And it gives us 55.2178, or 55.2. So let's go back to the document and work this out. So we have this, it is equal to 55.2 to 3 sig figs. The next question, we're asked to find BEM. So what is BEM referring to? We start at B, we go to E, then we go to M. So we're asked to find this angle right here, this theta value. Okay, so BEM. Since we have a right angle triangle right here, we should be able to use SOHCAHTOA, or just our trig ratios. So once again, we have SOHCAHTOA TOA. Any of these should work, but since we have this as an exact, this 45, we have the opposite, and we also have this given as an exact value. This 55.2 we actually found out using Pythagorean theorem. Might be a little inaccurate, shouldn't matter, but we have the opposite, we have the adjacent side. So opposite, adjacent, let's use tan. So let's go ahead. Tan theta is equal to opposite over adjacent. Tan theta is what we're solving for. Tan theta is equal to opposite over adjacent. And we can work this out using a little algebra. And if you want, of course, you can write it out as theta is equal to tan inverse 45 over 32. Or we can, of course, just end solve for theta. Okay, let's, what can we do? Let's go to the calculator screen. Actually, I'm actually just going to work it out on the calculator that I have beside me. And that should be okay. Tan inverse 45 over 32. And it gives us a value of 54.58, or we'll write theta is equal to 54.6. 54.58 is 54.6 to 3 sig figs. Just remember when you're doing these, especially at the beginning of an exam, make sure you are in degrees and not radians. So degrees in the top right corner of your calculator. Okay, moving on. Let's go to part C. Hence find the length of AB. Okay, so the length of arc AB rather. I'm going to clear away some of this and just write what's essential. All right. So what do we know? We know that this theta value was equal to 54.6 degrees. And if we want to find the arc of AB, we want to find this angle, or sorry, not this angle, this length that we sweep through, this portion. This is given to us in the formula booklet. I'm going to write it out here, however. This is arc length. Arc length, if we know if we have a full circle, our circumference, or essentially the perimeter of our circle, is given by 2 pi r. But if we only have, let's say, a portion of this circle, and let's say this is the center, and we only have a portion of our total circle, the question is, well, how much of our circle, if we want to just find the circumference, how much do we have? Well, we know a full rotation is 360 degrees. So if we're talking about the arc length, we only have, well, a portion, theta over 360. We've only swept through a portion of that 360 degrees. So arc length is theta over 360 times the circumference, a full rotation, but we don't have a full rotation. We have a partial rotation. So find the length of arc AB. What do we need to solve for? We need to find r and theta. We already know we have this value, 54.6. So if this is equal to this side length right here, and this side length right here, because this was the midpoint. So we know that this, sorry, we also know that this is the midpoint, and this is the midpoint, so these two are the same. And since they share this side, we actually have two equivalent triangles. So if this side length right here is 54.6, we know that this as well will be equal to 54.6 degrees. So in sum, what angle do we sweep through? What fraction of a whole do we have? Well, we have 54.6 times 2. So if we wanted to find this whole theta value, let's just call this 54.6 times 2. 54.6 times 2 is given to us by 109.2. That's correct, yeah. So this whole angle that we sweep through is 109.2. Alright. So we've got this part, 109.2 over 360. That's a portion that we've swept through, portion of our circumference, I guess, that we're dealing with. And we want to multiply this by 2 pi, and then r. R is our radius. So remember, we're sweeping through this angle, and this distance from the center to the edge of our circle is going to be our radius. So we know that the radius is equivalent to 55.2. There it is. That's our radius as well. So 2 pi times 55.2. Okay, that should give us our arc for AB. Let's go into the calculator and find the value. Okay, so we have 109.2 over 360, and we want to multiply this by 2 times pi. Whoops, sorry, we don't need that. 2 pi, and then the radius we said was equal to 55.2. Okay, and this would be our arc length, 105.206. Let's go back to the document. So 105.206 to 3 sig figs will just be 105. Okay, let's keep going. The outer edge of the track from C to D is also a circular arc with center E, such that the track is 4 meters wide. Calculate the area of the curved portion of the track ABCD. Alright, so outer edge of the track from C to D is also circular. So from C to D, this is also a portion of a circle, and the track itself, the width of this track is 4. And we're asked to find the area of the track. That is to say, this portion of the track right here. So the total area right here. This is what we want to solve for. Okay, so that's kind of an interesting question. So we just had arc length. Now we're asked to find the area not just of a sector, not just of a fraction of a circle, but we're asked to find this portion right here. So we want to find this right here. So the question is, how can we essentially find that? Let's draw a diagram and see what we can do. So here is a circle. And if we have just a portion of a circle, let's say here's our center, then we have a portion of a circle, that would be the area of a sector. So area of a sector. Area of a sector for some theta, so some portion of a circle. So we know again, to sweep out a whole circle would be 360 degrees. But we don't have a whole circle, we just have theta over 360, a portion. And the total area of a circle is given by pi r squared. Area of a sector is given to us in the formula booklet as well. And so in this case, we want to find not just a sector, we want to find a fraction of a sector, which makes it a little more challenging. But if we imagine that this is this green area that we want to solve for, and we have this blue area right here, what we can do is we can find the area of this larger sector. I'm going to highlight it. So we can find the area of this larger sector, but we don't want all of it. We want only what's within. So what we can do is we can take this area out on the inside. So let's say the area of the green, which is the larger sector, let's call it area of the green, minus the area of the blue would give us just the area of, let's just call it the track, I guess, the area of the track. So how do we find the area of this blue section right here? area of this blue section, we have, actually sorry, let's find the area of the green first. I think that'll be better. So we have this larger track right here. Let's find the area of this larger track. Area of a sector is given by pi r squared times theta over 360. We're still sweeping through an angle of 109 degrees. So for the area of the green triangle, it's going to be still 109.2 over 360 times pi, and then what is the radius? So the radius of this smaller circle was 55.2, and how do we find the area, or sorry, the radius of this larger circle? Well, we know the track is itself 4, so if we're traveling 55.2 from here to here, and we travel another 4 meters to complete this radius, we would travel 55.2 plus 4, or you would travel a total distance of 59.2. So pi r is 59.2 squared, pi r squared, minus, and the area of the blue sector is again going to be 109.2 over 360. So the portion that we've swept through is 109.2 degrees. Actually, I don't know why I wrote 109.2 instead of 109. Generally, we want to preserve as much accuracy as possible, and since they never asked for 109.2, and they just asked for this 54.6, generally we want to preserve as much accuracy as possible, so 109.2 is actually not a bad idea. Okay, 109.2 times pi, and then the radius is, we already found it to be 55.2. This is the radius of the green, and this one right here is the radius of the blue. Okay, so it's going to be 55.2 squared, and all of this should equal the area of the track. So we've got some sector, but we don't want the whole sector. We want to subtract a portion out of that. So we can find the area of the larger sector, which is this green one right here. This larger green one, which includes the blue, right? Which includes the blue. And then what we're going to do is we're going to take the blue portion out. We're going to remove this, which is given by this formula right here. Okay, so looks kind of intimidating, but conceptually I don't think it's going to be too bad. We've got a slice of a circle, only a part of our circle, and we want to remove a section of that part itself. So larger area minus smaller area to find what remains. Okay, so let's go to the calculator screen and work this out. Okay, so let's set a fraction up, 109.2 over 360. We're going to multiply this by pi, and then the radius itself for this larger one was 59.2. We want to square that, and we want to take away the smaller circle. The smaller circle as well was 109.2 over 360 multiplied by pi, and then the radius of this was just 4 meters less. Okay, and that should give us our area, 436.07 meters squared. So let's go back to the document. So the area of the track is then equal to 436.07, or just 436 meters squared. Okay, not too bad. Calculate the area of the curved portion of the track. I'm going to write it here because I believe we'll need it later. 436 meters squared. Alright, last part of this question. The base of the track will be made out of concrete that is 15 centimeters deep. Calculate the volume of concrete needed to create the curved portion of the track. So we want to find the volume, and it's going to be 15 centimeters deep. What's going on here? And let's see, why is it a 3-mark question? So here we've got the track itself, right? So we've got this curved portion of the track. And what we want to do is we want to pour some concrete within this track. So let's say we've got something like this. I'll do my best to potentially draw this curved portion of the track. We want to pour some concrete along here. I think that's okay, I guess. And what we want is we want the concrete itself to be, if this is the height, I think I can actually do a better job. I'm going to try to do a slightly better job of this diagram because I think it may be important. Okay, so we've got this volume. Volume is, of course, just going to be our... Oh my goodness, what is going on? What is going on? That's fine, I suppose. So we've got this portion of our track, and this is part of our track right here. And this is, of course, a little accentuated, but if we know the area of our track, and we want to, this is just a section of it, and we want to have a volume of 15 centimeters. Volume itself is just length times width times height, or area of the base times height. So if we already have the area of the base, we should be able to just multiply it by the height and be done. But why is this a 3-mark question? Our track itself has an area, so the area of the track has an area of 436 meters squared. But, and this is where, not exactly a trick, but maybe where close reading matters, this is given to us in centimeters. So sure, volume is simply equal to area of the base times height, but the area of the base is 436, and it's in meters, and the height itself is in 15 centimeters. So we need to convert our centimeters to meters. We know there's 100 centimeters in a meter, so 15 over 100 means that we only have 0.15 meters. So there we go, 0.15. And that should give us our volume. Area of the base times height. We know the area of the base of this track, and we want to stack it up with 0.15 meters of concrete. Okay, I'm going to work that out on the calculator that I have beside me. And we have it as 65.4 meters cubed, so cubic meters. Alright. So maybe kind of a tricky question. Yeah, I suppose this 3-mark is some indication that there's something more going on than just area of the base times height. Even so, 3 marks might be a little high. So convert your 15 centimeters into meters. And just so this is clear, 100 centimeters is equivalent to 1 meter. And so if we have 15 centimeters is equivalent to what? Well, what can we multiply? Actually, let's ignore that kind of. Let's keep it as 100 centimeters is equivalent to 1 meter. Alright everybody, I hope that was helpful, and as always, best of luck. Take care.